Okay, so let's talk about tomorrow's quiz. You got quiz 3. Quiz 3 covers chapter 6. And so you are responsible for knowing the normal distribution and binomial distribution. Okay. And I have posted a practice quiz 3 on CCLE. So if you go to week 6, there's a Stats 10 quiz 3 practice and quiz 3 practice answers. So you can try it out tonight. Just make sure you got a handle on this. And I figured I'll do a couple like a practice problem here, and then and if you guys have any questions on this stuff, I'm happy to answer them. All right, there's one more type of normal distribution problem, which I have not covered, and so I'll cover that right here, okay? So this is just it's basically another normal distribution problem. But this time you're looking for the area between two values. So for example, we'll say diastolic blood pressure, and I'm making these values up here, okay? So you get blood pressure and it's like 115 over 75 or something like that. Okay, we'll say diastolic blood pressure, we'll say comes from a normal distribution. So we'll say normal distribution with mean equal to 75 and standard deviation equal to 12. I'm just kind of making numbers up here. And the question is, what is the probability that a person has a blood pressure, we'll say between 72 and 90. What's the probability someone has a blood pressure between 72 and 90? And so the way we are going to answer this, I'll draw a picture here. So I've got this curve. And in this curve, I'm going to put 75 right here in the middle. 72 is smaller than 75, so it goes to the left of 75. And 90 is bigger than 75, so it goes to the right of 75. And the way we're going to solve this is by doing this. Okay, and so I'm going to say the area to the left of 90 minus the area to the left of 72 equals the area between 72 and 90. So do we see that visually? We say if we take everything to the left of 90 and I subtract off the part that's left of 72, then I will have the part that remains, which is the area between 72 and 90. Okay, and so this is not too bad. All we have to do is we just have to find the area to the left of 90, the area to the left of 72, and then we take the difference and we get the area in between. So I start off and I say z is equal to, I put 90 in the middle, and then I subtract off the mean of 75, divide by the standard deviation 12. What do I get? 1.25, is that right? Okay, so I get 1.25 over here. And the area to the left of 1.25 is, so I look up 1.25 on my table and I find 0.8944. That's all of this over here. 0.8944. Okay, next part, find the area to the left of 72. 72 minus 75 divided by 12, I get negative 0.25. And the area to the left of that, okay, the area to the left, I look up on my table, negative 0.25, 0.4013. Okay, therefore the area between, so this part, 0.4013, area between is 0.8944 minus 0.4013, and that's going to give you 0.4931. And there's my answer. This part is 0.4931. Okay. All right, so just under 50%. Yeah, question.
Do we leave it in decimal form, or do we then write it like 50%?
Well, I mean, you can leave it. You can leave it in decimal form. Okay. I mean, if it asks what percentage, then you would probably say 49.31%. And that's probably fine. Another question? Yes, yes, of course, you should use the table for the quiz. Don't forget to bring your table to the quiz, okay? Make sure you bring the table to the quiz. Yeah, I don't expect anybody to have this memorized. So yes, use the table for the quiz, please. Okay, any other questions? We're good with this type of problem? Okay. Then let's take a look at the binomial distribution. We'll do a binomial problem. Okay, so right now the NBA playoffs are going on. I'm a fan of basketball, so and there's a player, Steph Curry. I don't know if you guys are fans or not, but he's one of the best shooter, if not the best shooter in the league. Okay, it's debatable, right? But everything's debatable. But so Steph Curry is, we'll say, is a 91% free throw shooter. Okay, I think this season it was just below. It's like 89.4 or 90. I don't know. It hovers somewhere around here. Okay. And so, let's say in a game. Well, first of all, let's say that free throws are independent of each other. perhaps that's a dubious assumption, but we'll say that they are. And so if you don't ever watch basketball, you have no idea what I'm talking about. In basketball, the goal is to get the ball into this hoop, right? and a free throw is awarded to a player if if they're fouled while they're shooting or something like that. Then they are allowed to take 1, 2, or 3 shots at the hoop without any kind of distraction. Well, no distraction from the players. And so generally, the shooting percentage is relatively high compared to the rest of the game where there's active defense going on. And your top elite players for free throws will be in around 90%, okay? Where you'll have other players who maybe shoot 50%, and they're known more for slam dunks or something. Okay. So let's say that free throws are independent of each other, and we'll say let's say Steph Curry will take 9 free throws in a game. All right, so here's your first question, and we'll make a clicker question out of number 2. Okay, so question 1 is, what is the probability that he makes 8 out of 9 free throws? Okay, and the clicker question will be, what is the probability he makes at least 8 of the 9 free throws? And probably you'll need to answer the first one to answer the second one. Let me put down some answer choices here. Oh, okay, and sorry, let me get the, okay, so those are your answer choices. Let me get the clicker software running. Okay, go ahead and work through this. If you need to talk to your neighbor, you can talk to your neighbor about the answer. And if you're watching online, I'm going to pause the video here. So get your clicks in. Click, click, click. Okay. All right, let's see. The correct answer is C. All right, well let's take a look. Let's take a look. What is the probability he makes 8 out of 9 free throws? Okay, so probability he makes 8 out of 9 free throws. This is a binomial problem, so we're going to do 9 choose 8, 8 out of the 9, and then he has to succeed his probability of making the free throw is 0.91. This has to happen 8 times, so it's going to be 0.91 raised to the 8th, and the probability that he misses one happens with probability 0.09, and that has to happen 1 time, right? So when I punch this into my calculator, I get 0.3809. 0.3809. All right. What is the probability he makes at least 8 of the 9 free throws? At least means 8 or more. 8 or more. And 8 or more means when you take 9 free throws means 8 or 9, okay? You can't have 10 because you only took 9 free throws. So it's 8 or 9 in this case. And so what we have to do is we're going to do the probability of 8 or 9 is equal to the probability of 8 plus the probability of 9. And is there any overlap I have to subtract off? No, because if he makes 8 out of the 9 free throws, he cannot have at the same time also made 9 out of the 9 free throws. So there's no overlap for us to subtract off. Okay, we calculated the first part already. Probability of getting 8 out of the 9 free throws, we found this to be 0.3809. And the probability of getting 9 out of 9 free throws will be, what, 9 choose 9 times 0.91 to the 9 times 0.09 to the 0. Okay, this simplifies 0.3809 plus 0.4279. Okay. So this actually says he is more likely to make all 9 out of 9 free throws than he is to miss one of them. And this gives us a total of 0.8088. So the correct answer is C. Answer choice A was just 0.91 raised to the 8th. And this is not correct because this is the sequence, I don't know, you make the basket 8 times. This answers only the probability of making the basket 8 times in a row. Okay, which is different from making 8 out of 9 baskets. This is the probability of making 8 baskets in a row, and doesn't account for you know, the last basket, whether that's a miss or a make. Okay. Question. So if it's binomial, okay, it's binomial if the order does not matter, okay? Binomial if all that matters is how many successes, and not when the order, not if order plays a role, okay? So binomial when order does not matter, and you are only interested in the number of successes. Okay, so you know, generally in sports, we only care about the end score. Okay, it doesn't matter if all the points came in the 4th quarter or the 1st quarter. It's just, you know, who got more points type of thing. Okay, so if you're only interested in you know, how many times we make the basket, then that's going to be a binomial situation. If it says, you know, what's the probability that we make the first 2, but we miss the 3rd, and we make the remaining ones, then that's not a binomial problem. That one, you have to have the exact sequence of events. So it's not binomial if the exact sequence of events matters. All right. Any questions on this? There is one more aspect about the binomial distribution, and this is the kind of the mean and the standard deviation of a binomial distribution. And this makes an appearance on your homework. The mean of the binomial distribution is equal to n times p. And I think this makes intuitive sense. For example, if we flip a coin 100 times, and the probability of getting heads is 0.5, how many heads do we expect to see on average? How many heads will we get on average? Or what is the mean number of heads? Well, that's going to be 100 times 0.5. We would expect to see 50 heads out of 100 flips on average. I think that makes sense, right? The standard deviation, not as intuitive, and I'm not going to bother try to derive this for you, but this is a good, now I hesitate to even put this up here because I fear this will only confuse us later. But it's just n times p times 1 minus p. But this, this applies only to the binomial when we are dealing with counts. Okay. And in this case, we would say 100 coin flips, the probability of heads is 0.5, and the probability of not heads is 1 minus 0.5. That's what we have. And so this becomes the square root of 100 times 0.5 times 0.5, which is the square root of 25, which works out nicely to 5. Now this is often not the case. Oh, if p was 0.6, it would be the square root of 24, which is, I don't know what that is, 2 root 6 or something. So that's what we have. Okay, that's the standard deviation. I'll ask the TAs to put these formulas up on the board when you guys take your quiz, because there's a question that asks this thing. Okay, but it's just a matter of just identifying what n and p are and then plugging it into the formula. It's pretty easy. All right, is that good? Okay, because now I'm going to start chapter 7. So I just want to make sure we don't have any questions before I go on. Did everyone have a good weekend? Yeah? Great. Okay. I hope you guys have a good weekend every weekend. Actually, I hope you guys have a great day every day. So even if that means you have a quiz tomorrow, I hope today is a great day for you. Okay, chapter 7, sampling distributions. Of course, not every day is great, but yeah. All right, a sampling distribution. This is the topic of chapter 7. What is a sampling distribution? Let's see. Well, I'll put it like a loose definition here. Okay, sampling distribution is the distribution of all the possible values of a sample statistic for, we'll say, random samples of a certain size. I hope you're okay. All right, so let me, so we'll start with that definition, and then I'll try to explain what this means. Or maybe this just makes sense straight up. Okay, so what is a sample statistic and how does it differ from a population parameter? Okay. Well, the population parameter, this is a property of the population. Okay. So remember, in statistics, we said kind of the goal that we are trying to achieve in statistics is we want to make conclusions about the population based on limited data. We're saying the population is too big for us to try to study directly. So instead, we take a little sample out of the population, and we're hoping this sample is representative of the population that we're interested in. And by studying, the people or the things in our sample, we're hoping we can just generalize and make conclusions about the population. So one thing that we might make conclusions about is the population parameter. This is a property of the population. This is generally it's unknown to us, but this is something like the mean of the population. The mean of the population, such as we'll have the symbol mu, or this the proportion. Okay, so I'll say the population proportion. And that will be the letter P. Okay. And meanwhile, a sample statistic, this is a summary value for a statistic. I'm sorry, summary value for a sample. So we draw, we take a random sample out of the population, and we can calculate the mean of a sample, the sample mean. And we would get X bar, or we would get the sample proportion. And we have P hat for the sample proportion. And the sampling distribution is the distribution of all the possible values of a sample statistic for random samples of a certain size. All right, let's try to break that down. Okay, can I flip to the next page here? No? All right. How about now? All right. Okay, that's all right. That's all right. My daughter's one of my favorite. She's 3.5. She likes to always say, "Not quite yet." You ready to go home? Not quite yet. Can I turn off the TV? Not quite yet. All right. I'm gonna count to 30 and I'm gonna turn off the TV. Oh, okay. Well, anyway. I don't know why I'm telling you this. Okay, I'm gonna go anyway, so it's all right. All right, let's say I decide to fill a giant, this is a tub, and I'm gonna fill it with Reese's Pieces candies. You guys know what these are? These are like, they look like M&Ms, but they have peanut butter inside, and they're all right. They come in 3 colors. You can get orange, yellow, and brown. All right. And okay, so let's say I fill this up. I don't know, okay. All right, so this is going to serve as our population. And I'll say I have so let's say we count all of the pieces in the candy, in the bucket. We count all the pieces in the tub. And let's say, we count 15,490 pieces. All right, and then for simplicity, I will say, and we found exactly 4,647 orange pieces. Okay, and so our proportion of orange in the population is 4,647 divided by 15490, and this is exactly 0.3. 0.3. Okay, I picked it just so we have a nice number. You're probably not going to get such a nice number in real life, but okay. So in the population, this is exactly 30% orange, and if I stir up the tub and I draw out a piece of candy, I have a 30% probability that it's orange. And we'll say, if I take just a little scoop, we can pretend that each of those pieces of candy are independent and have a probability of 0.3. Technically, it's not exactly the case, right? Like if I draw the first one and it's orange, then there's technically 4,646 orange pieces out of 15489, and the proportion that's orange changes ever so slightly. Okay, so technically it's not, but we'll say that the change is negligible. Okay, so we'll just pretend that I draw a bunch of pieces of candy at 30% orange. I think that's okay, right? So let's say I have this little scoop. Okay, this is a scoop, and it's going to pull out, every time I scoop, it's going to get exactly 50 pieces of candy. Okay, so it gets exactly 50 pieces of candy. All right, so I stir up the thing and I pull out a scoop of candy, and my first sample 1, let's say I'm going to get 50 pieces of candy, and let's say I get 16 orange pieces. Okay, so what is my sample proportion that's orange? My p hat is 16 divided by 50. It's 32% orange. Okay, all right, I dump this back in and I stir up the tub, and I repeat this again. So now I go to sample and I get sample 2. I get another 50 pieces of candy. This time I get 12 orange pieces. Okay, and so my p hat this time is 12 divided by 50, only 24% orange. Okay, and then I repeat over and over again. And every time I take a scoop of 50 and I count how many orange pieces I get, and I'm going to keep track. We keep track of all of the different p hats we observe. Okay, we keep track of all the values of p hat we see. Okay, and ultimately, I'm interested in the distribution of p hat. What kind of values of p hat appear frequently? What values appear infrequently? What values of p hat never appeared? Okay, that's what I want to know. I want to know the distribution of p hat. And that's going to be my sampling distribution. We want to know the distribution of p hat. Okay, and that is my sampling distribution. Does that make sense? We're going to just repeatedly draw pieces of candy. So we know that the population is exactly 30% orange. So what do you think will be common values for p hat? if we know that the tub is exactly 30% orange, and I go in and I scoop out 50 pieces of random candy, 50 random pieces of candy, and I dump them out and I count how many are orange, what do you think would be a very common value of orange pieces? Yeah, 15 or 30% orange, right? We would expect something around 30% orange. But, you know, is 16 out of 50 or 32% orange going to be common? Probably, right? Okay. What about 40 out of 50, so 80% orange? Do you think that will happen? I mean, it's technically not impossible, but it's probably not going to be a common occurrence, okay? It'll be very, very infrequent. All right, we have a website that simulates this, okay? Reese's Pieces, Reese Witherspoon movies, okay. What was she in recently? I don't know. I can't. You know, from Legally Blonde. Okay. All right. So we will say that the probability of orange in the population is 30. We're going to draw out 50 pieces of candy, and I'll run the simulation. And what it's doing is it's taking the orange pieces and it's putting the orange pieces over here, and it's putting the yellow and brown ones over here. And in this case, we counted 10 out of 50. So we have 20% orange, and we're going to put a little dot here at 0.2. We're going to keep track of all of our values we observe by building up a dot plot. So I'll do this again. Okay, so in this scenario, we counted 16 pieces that are orange. That gives me 32%, and we put a dot at 32. Let me just kind of speed this up. And here we get 15 out of 50. That's 30% exactly. Here's another sample. This one came out 18. We have 36% orange. Okay, and we can keep repeating this. There's another sample where we got 36% orange. And so we can see, and here's another sample where we get 32% orange. And so after taking 6 samples, these are the different values of p hat I've seen. I've seen 36% twice, 32% twice, 30% once, and 20% once. Okay. I can do a few more at a time. Here I can do 10. So this is going to throw 10 dots on the board. Okay, and we get these are the different values I've seen. Here's another 10 dots. Okay, here's another 10, and we can start to see some values. I'm going to just do 100. Okay. So after now I've done a total of 146. These are this is kind of the distribution of all the different p hats I've seen. Okay, and so I'll just do a few more. Okay, and we can see that so this is now after 346 samples. We can see that some of the dots are super close together, that these will effectively just merge into straight lines. Okay, but that's all right. The relative heights of the lines will give us an idea of which values have appeared most commonly. So far, after 346 samples, 32% has appeared the most frequent. 30 and 28% are quite frequently, and 26% is also frequent. Okay, but we've also gotten values as low as 12% and values as high as 48% so far. I'm going to do 1,000 values. Okay, this is our distribution after 1,000. Our distribution after 2,000, after 3,000, and let's just say we're going to do 10,000. So here's my distribution after 14,000. This is my distribution after 24,000 random samples. Okay, so this is simulating doing 24,000 times. I'm scooping out 50 pieces of candy, counting them up, and then dumping them back in. Okay. And so after 24,000 or so samples, what we see is that the values 28, 30, 32% appear most commonly, okay? And values as low as 12% or maybe even 10% can appear, but very infrequently, okay? And what does this shape look like to you? It looks quite normal, right? This is we've got a normal curve that that can be superimposed on it, and we see, you know, kind of this unimodal and symmetric shape. All right. Let me just do another batch of samples. So let me put this into our notes here. Okay, and here's the web address if you are so inclined to explore this yourself. You guys don't do this for fun? Okay, and so the idea here is, in this case, we know that the population has proportion 0.3 orange. Okay. And so, you know, when we take samples, okay, we expect our samples p hat, our random sample, to have a p hat close to 0.3, but maybe not exactly so. We expect our random sample to have a proportion p hat that is close to 0.3, but not, you know, but not necessarily exactly. It could be 0.3, but it's not necessarily. So, you know, our most recent sample has 17 orange out of 50 pieces, or p hat equal to 0.34. Okay. After many samples, okay, we keep track of all the p hats. Okay, and you know, we can see our sampling distribution. And so what it appears so far is that our sampling distribution is unimodal and symmetric. And we'll talk about the exact shape of the sampling distribution on Wednesday. So we'll end here for now, and we'll see you guys on Wednesday.